Hey, everybody, this is Tom Dean. I'm a field engineer here at Buoyant, and I've got Flynn with me. And today, Flynn is going to talk about IP6 and Linkerd.
Excellent. As we get started, if folks want to let us know that you're here, that would be good. And I think we have a pointer to the work. Yes, there we go. The best place for questions is the workshop channel on the Linkerd community Slack, slack.linkerd.io. Probably many of you are familiar with this workshop channel already, but just in case. All right, let's get to it then. We are here to talk about IPv6. Brief words from our sponsor beforehand. That we have a book out, Linkerd up and running. That's by me and Jason Morgan. So hopefully we got it right. If not, check it out. Let us know where we screwed up. And for the agenda here, we are going to be doing, honestly, this slide says a quick discussion of IPv6, but it's going to be maybe a little bit less quick. I guess we'll find out. And then we're going to go into a demo of using Linkerd with IPv6. So if you want to follow along, you can go to the IPv6 directory in the Service Mesh Academy repo. Please note, it requires Linkerd Edge 24.5.5 or later. Do not try it with anything before 24.5.5, or you can get very, very confused. Another thing that's interesting is that this is the first time that we've switched from using K3D to using K3D for local clusters to using kind for local clusters. This is because K3D doesn't support IPv6 yet. I assume that eventually they will, but for now we're going to stick with kind. Kind actually turns out to be kind of nice. One other note, the way this demo is set up, I actually set up kind and then I set up load balancers in kind because I really, really don't like using port forwards with multiple clusters. If you are on a Mac and you were using Docker Desktop for Mac, this is not going to end well for you. I'm sorry about that. Some time ago, I switched to OrbStack. It is much more graceful about networking than Docker Desktop for Mac is. Highly recommended. So IPv6. And again, as usual, if you have questions, you can drop them in the chat here, or probably better to drop them into the workshops channel on the Linkerd Slack. All right, V6. If we look at a little bit of history here, the internet gets rooted in a suite of protocols that are ultimately all derived from the Internet Protocol IP. IP version 4 is very, very common right now. It was standardized by RFC 791 in September of 1981. It is 43 years old almost. It was a little disturbing to look up that particular fact. Also, as we talk about IPv4 and IPv6, please don't get too hung up on those specific numbers. We could have a longer discussion about what happens to 1, 2, 3, 5, 7, etc. But the short version is V4 is the current standard and V6 is the new standard for reasons. V4 is the one that has 32-bit addresses, and you see dotted decimal notation that probably everybody is familiar with. So you see addresses like 172.31.4.64. And we also can talk about network ranges, which have the fancy name of CIDR, with things like 172.31.0.0/16, meaning 16 bits. The first 16 bits of that are interpreted as a network, and the remainder are interpreted as an interface within that network. For those of you who have not, in fact, been using IP since the 80s or 90s, the CIDR abbreviation stands for classless internet domain routing or something along those lines. The classless part comes from in the beginning, the leading 8 bits would determine a specific class of your network. And we got rid of that idea when it turned out to be a bad one over time. Okay, IPv4 has this minor problem that the world has run out of IPv4 addresses. Asia Pacific actually ran out in 2011. Latin America and the Caribbean ran out in 2014, North America in 2015, Africa in 2017, and everybody else in 2019. So this is not a problem that is going to be a thing. This is a problem that is already a thing. And when I say ran out, what I mean is if you go up to your ISP and you say, hey, I'm starting this awesome company, I'd please like a globally routable block of IP addresses, they may very well look at you and laugh. Or they'll come back and say, that's cool, but you're going to have to wait for somebody else to give us some address space back before we can do that. So this is a very real problem. If you want like 1 or 2 addresses, fine. If you want a big, larger global block, much, much less fine. And to everybody who's going, oh, but wait, there are 4 billion IPv4 addresses. How can we possibly have run out? That would be because there are many more than 4 billion things on the network right now. The Internet of Things, as of late 2023, was estimated to already have 17 odd billion things on the network. So yeah, this is a problem. The way we are still using this is by not requiring everything on the internet to be reachable from everywhere else on the internet. And the standard part of this goes back to RFC 1918. Oh, thank you. The standards on this go back to RFC 1918, which happened in February of 1996, which should tell you how long it's been recognized that the IPv4 address exhaustion thing was a problem. RFC 1918 took 3 specific ranges of IPv4 addresses and said, these ranges here are kind of defined to be private things that must not be routed on the open internet. So if you're using something in the 10/8 range, you can't route that beyond your router, basically. Anybody can use these for anything. There's an underlying assumption that network address translation is just going to work. Sam says, it's fine. We'll just carrier grade NAT everything. Yeah, basically. We're not going to talk about carrier grade NAT today because it is a terrifying, terrifying concept if you take it too far. But yeah, the assumption behind RFC 1918 was that it was okay to do these private ranges because you could just NAT to talk to the global internet from inside your private range, and nobody needed to talk to your private range on the way back in. And this, kind of basically works. Basically, you get into big problems with 1918 when you're trying to do things like use a VPN while you're sitting in a coffee shop that happens to use 10/8 and your corporate home office also uses 10/8, and everything falls apart, nothing will work, and there's fundamentally no way to fix this problem with IPv4. Not you understand that this is a problem that has ever happened to me personally. Yeah. So since 1996, which if you do the math, 28 years ago, more and more of IPv4 has been falling into the RFC 1918 range, which means less and less of IPv4 is globally routable in the internet at large. Specific place that probably everybody on this call has actually used 1918 without thinking about it is if you look at the pod CIDRs of a Kubernetes cluster, they're pretty much always RFC 1918 addresses. Okay, IPv6 came about to deal with this problem, largely to deal with this problem. I'd like to point out the reference up there is to RFC 8200 in July of 2017. Please do not mistakenly get the impression that IPv6 is a recent thing. 8200 updates RFC 2460 from December of 1998. As Alejandro at Buoyant put it, we're dealing with cutting edge 26-year-old technology here. Alejandro is he's the engineer who did most of the work on V6. He gets huge props for how good it is. It's really amazing. V6 does tackle some other really important things. It deals with extensibility at the protocol level of IP and makes it better. It has some simplifications to the base protocol. It includes standardizations of authentication and integrity checks and stuff like that, which were optional in V4. But the IPv4 address exhaustion is the really big thing that V6 is tackling. Fun fact, the US government has actually mandated 80% uptake of IPv6 by the end of fiscal 2025, which is very close to now. Okay, V6 deals with the address exhaustion thing by expanding the address from 32 bits to 128 bits. It also requires CIDR when you're talking about ranges instead of messing with classes, which is kind of nice. When you write an IPv6 address, you do it as 4 hexadecimal digits separated by colons. So these are two specific types of IPv6 addresses. The upper one, actually, you know what? We're going to talk about the specific special address ranges later, but the upper one, just for entertainment value, is from a kind cluster on my laptop, and the lower one happens to be one of Google's addresses, like www.google.com's addresses. If you have leading zeros in a group, you get to remove those to make it shorter. So you could write those addresses this way. And since those runs of 0 bytes are 0 16-bit groups, it's pretty common for IPv6 addresses to have runs of zeros. So you get to replace any single run of zeros in the address with a double colon. So this is the way you would actually see those addresses written in practice, just because that first form with all the written out zeros is just far too ugly to contemplate. Now, there's also a new quad A DNS resource. So if you do an IPv4 lookup in DNS, you're actually asking the DNS for the A address record associated with the name that you want. Since the address is 4 times as long, they decided to name the resource quad A to get a v6 address out of the DNS instead of a v4 address out of the DNS. Basically, every DNS system in the world today, it being 2024, knows how to deal with quad A's. It's just not a problem anymore. 128 bits is gargantuan, and if you are used to v4, this actually can sort of mess with your head a little bit. The smallest allocation that an ISP is supposed to make if you ask for a range of v6 addresses is a /64. So there's 64 bits of network and 64 bits of identifier within the network. 64 bits within your network is enough to reproduce the entire IPv4 internet 4 billion times over. Providers are also encouraged to give out /48s whenever you want them. A /48 is big enough that you could give 4 IPv6 addresses to every star in the universe before you ran out, which, like I said, if you're used to v4, this is just weird to get used to. In fact, if we were to give a 48 to every human being on the planet and keep doing that as new humans were born without recovering /48s, we would run out in something like 450 years. So yeah, just don't worry about address space with v6. Don't ever worry about address space with v6, and don't be thinking in terms of, oh, how do I conserve it? Just don't bother. Just do things that are convenient. So let me also remind everybody again, questions can go here or in the workshop channel. I am going a little bit quick on this one, but sing out if something seems odd. Tom, that goes for you too. Anything, so when you write a program these days with IPv4, you'll often tell it things like, hey, I want you to bind to 0.0.0.0, meaning I don't care where a connection comes from. I want to accept all of them. The anything address in v6 is written : and it is again the address with all 0 bits. Localhost, the loopback address is : 1. None of this 127 dot business. There's a thing called a unique local address where the upper 7 bits are FC. The lower half of that, FC00::/8, is technically a reserved address space, but fascinatingly, Kind uses it for local addresses. I'm not quite sure why Kind does that. However, these ranges, these are things where the standard has changed over the last 5-10 years. So we could easily be dealing with something where Kind did something because that was the way that it was specified in an earlier rev, and Kind hasn't been updated yet. FD00::/8 is a locally assigned unique address, meaning you can use it. They are supposed to be globally unique addresses, but they must not be routed past your main internet router. So they kind of act like RFC 1918 in that you can pick something in FD00::/8 and just use it without going to a registry. You are encouraged to pick random things and not try to use, zeros or anything like that. But the idea here is that you can use them without oversight. And even better if, like, you do this and then If you're working for a company that does this and then another company that does that decides to merge, hopefully you will have picked unique address spaces within FD00, and so you won't have to renumber the worlds during merges. One of the things that V6 sort of had in mind from the beginning is that addresses should be a little bit more portable than they used to be. Back in the days before RFC 1918, people tended to get a chunk of IPv4 address space from their internet provider, and if they changed internet providers, they would have to renumber the world. And one of the things that V6 wants to prevent is that. There's a link local range, FE80::/10. If you look over any modern operating system and you do ipadder show or ifconfig-a, depending on your operating system, you are very likely to see a bunch of things with FE80 prefixes. These are things that get assigned pseudo-randomly to identify a particular interface that get used a lot during auto-configuration, for example. They're not really routable addresses. You can probably use them on the same machine. You can maybe use them on the same network segment. I personally would not really try to use them for anything beyond auto-configuration. There's also the multicast range, FF00::/8. I'm not going to talk about multicast today, even though it's really cool. IPv6 also defines a thing called anycast, which is even cooler, but we're not going to talk about that again. So anything that's outside this range is supposed to be a globally unique, globally routable address. So also URLs change in IPv6. So with IPv4, you just say http://172.31.4.64. But in IPv6, you put the IPv6 address in square brackets because you need to be able to distinguish the IPv6 address separated by colons from the port number, which is also separated by a colon. So this is a thing to remember as you start messing with this. All right. Any questions so far? Tom, anything come to mind from you with our Whirlwind V6?
Yeah, I like the fact that you pointed out that you have to use the brackets because again, that is something that in deploying lots of nodes years ago, I ran into. You have to respect the special separators and characters in your automation.
Yep. I am not going to lie. I got burned by this 2 or 3 times trying to set up this demo where I forgot the square braces and nothing worked. Yep. And yeah,
this was proto days before everything was decorative. So it was very good learning experience on how to manipulate these things. Cause that's what we had to do. We didn't have Ansible and all those things back then. Right. So that's how old this is.
Yeah. It's
technology, right?
It's fascinating to be talking about this now when it's so old, but I remember hearing talks about this back in the mid 90s.
Yep.
Back when we naively believed that everybody was going to be able to quickly make a transition over to a V6 world. And, like, for example, I didn't talk about it, but there's a way you can have an IPv6 address that is encapsulating a V4 address, which was entirely in aid of this magical transition that never happened.
Yep.
Over, 20 odd years, because it is hard to get the entire internet to do anything.
Yep. Yeah. Somebody just got to wait until it's an emergency. That's all.
Oh yeah. That'd be, that's.
It's like taking a car trip with kids.
So speaking of this transition, this leaves us with 3 kinds of hosts in the world, right? We have IPv4 only machines. Candidly, the only ones of these that I see these days tend to be embedded systems, because pretty much all of the newer stuff in the world, all the bigger systems are smarter about this. We have IPv6 only hosts. In theory, anyway, I do not believe I have ever seen a V6 only host. I have been in a situation where my phone could not get a V4 address because the Wi-Fi it was attached to had too many nodes on it, and it had run out of V4 addresses, and it could only get a V6 address. So that was kind of interesting. That happened in 2011 in China, by the way. And most modern systems these days are dual stack. They can do both IPv4 and IPv6. and they end up being able to do some pretty fascinating things in that world. In the dual stack world, very, very important note that trips a lot of people up. IPv6 is preferred. In any situation where you have an available v6 address and an available v4 address, for example, a dual stack host will use the v6 one unless you go to a lot of trouble to tell it otherwise. Likewise with DNS, if you just say, hey, give me the addresses for this host, and you get back a quad A and an A record, if you're on a dual stack host, it will pick the quad A record first. All of the modern application languages support v4 and v6, and they do it really pretty gracefully. C does not count. C does not deal with this gracefully, but it's 2024. Don't write in C. For the love of all that is holy. All of the modern OSs are also natively dual stack. Linux, Mac OS, I'm pretty sure Windows. It just is just kind of not a thing to worry about anymore, again, unless you're in the embedded world. And Kubernetes has supported basically all three of these modes since Kubernetes 1.23. So it's kind of old in Kubernetes. One fascinating thing, though, as noted before, K3D, or K3S, I guess I should really say, does not support v6. So use Kind instead. It does support v6. And yeah, so I'm using Kind for this one, for the demo that we're about to get into. I predict I'm going to be using Kind for a lot more things later on, too.
Yeah, I ran into that doing other things this week. It's nice to have both of those tools in your toolbox. Remember,
really
too, that
is.
not all cloud providers
that's a great point.
IPv6 in their Kubernetes offerings, right? So make sure before you start doing all this planning and heading down this road that what you're running, if you're in the cloud, will support it, and the operating systems. See what kind of support they have, because it might be something you want to reconsider. If you're deploying on bare metal, you might want to replatform or do things like that. So again, 28 years, you would think everybody would be on the same page as this, but
flip side of that one is for the last, I don't know, dude, decade, I've been calling up. So at home, I have Verizon Fios and have for a long time. And for the last decade or so, I've been calling up Verizon every year or two going, do you route IPv6 yet? Jeez. And this year, they finally came back and said, yeah, your router should just be doing this. So now I have to go figure out what's up with my router.
Yep.
But, and again,
time for
28 years. Yeah, 28 years into this, you would expect that the routers would all just know how to do this, right? But it turns out the firmware on my router is kind of old, so I got to go upgrade it.
Yep.
You'll be pleased to know, Tom, that I decided not to upgrade my router right before this SMA.
That is a smart move.
Tom's point about cloud providers is very well made. I have to confess, I did not go and check on which cloud providers supported what and things like that. It's going to be out of date next week anyway, I'm sure. But yeah, good to look into that. Linkerd supports v6 and dual stack as well as v4 as of Edge 24.5.5. It is true that if you look at the release notes, you will see things saying that we supported it in 24.5.2, but don't use 24.5.2. Just skip ahead to 24.5.5. Basically, some of the earlier ones before 24.5.5 left IPv6 enabled by default in some scenarios, and that can cause trouble with some cloud providers and things like that. If you use 24.5.5, it's disabled by default. You can switch it on when you want it. That's where you want to be. Okay. One of the really fascinating things about this demo was finding out that it was challenging to figure out what to demo because it's almost completely invisible. It just works as far as Linkerd is concerned. Like I said, Alejandro, who is the engineer who did most of the work on this one, gets just massive props for that, because there are a lot of ways that the sharp edges could have been exposed, and I basically almost didn't find any of them. It was pretty cool. The one thing I found, if you're doing network authentication on dual stack nodes, you will almost certainly need to include both the v4 and v6 ranges to get network authentication to work correctly. And we're actually going to see that in the demo. Okay, I think this is the last slide before the demo. Why exactly should you do this? Actually, I lied. It's not the last one before the demo, but it's pretty close. Why should you bother going with v6 and such? Candidly, at this point, it's mostly future proofing. But future is closer than you are probably thinking. If we go and look into the crystal ball, IPv4 is probably going to stick around for a long time. And the reason for that is if you're dealing with tiny embedded Internet of Things devices, IPv6 is harder for them to run. And it's also harder to upgrade a big fleet of IoT things. So they may be stuck with v4 for a while, but nobody else has to be. We are already seeing the backbones trying to shift over to more v6 because, like Sam was mentioning, carrier grade NAT kind of sucks. So if they can shift over to v4 and just use globally unique addresses everywhere, their lives are made simpler. Likewise, cloud providers, even though it's not a done thing now, the cloud providers are shifting over to v6 because the cloud providers are adding more and more and more hardware. And so it can be easier for them to walk away from any concerns of thinking about running out of address space. And don't forget that business with the US government saying, hey, maybe we should be doing v6 because, they have a bunch of computers and they all need to talk to each other. So good reasons to go. All right. Demo. Everybody cross your fingers. So I'm actually going to be using 3 kind clusters to run this demo. I'm going to be running one that is only v4. And I'm showing you these kind configuration things. On the one hand, just why not? But on the other hand, I want you to notice that the pod subnet and the service subnet in my v4 only cluster have a 4 in them. 10.4.1, 10.4.2. And we'll go ahead and create that one. This is definitely one of those points in the demo where, I'm always torn doing these demos. Do I show them spinning up the clusters? Because spinning up the clusters takes some time, but I kind of like for people to see that I'm not actually just doing it all with smoke and mirrors. My v6 only network has a 6 in its pod subnet and its service subnet. The astute reader will also note that this is an FD00 address. So in fact, this is using one of those unique local addresses. Excuse me.
Kind of support YAML configuration files. I've been using it for the past week or so to test some CNI stuff and started to dig deeper. Yeah, I'm going to have parallel configurations for all my sandboxes so that when we run into something, it's not like, oh, now what do I do? It'll be like, oh, we'll just use this instead.
Well, fire it up. Yeah.
They both do certain things very strong, right? And there's definitely use cases where I love K3D. So,
yeah. My dual stack cluster has 2 pod subnets and 2 service subnets. And you'll also notice that they both have 10s in them because obviously 4 plus 6 is 10. True story, by the way, there is a draft RFC out there for IP version 10 written by a guy who picked the 10 because 4 plus 6 is 10. And the Internet Society apparently has gone on record as saying it will never move past draft. There's a bunch of really fun history to read in some of these things. Okay, so at this point, all of my clusters are running. I've got all 3 of them going. They're all attached to the same Docker network so that they can all talk to each other after we do some other stuff. Oh, hey. So Ravi over in the Workshops channel says that I am wrong, that K3S does support IPv6. So maybe it's just K3D that doesn't have a clean way to do it. All right, I'm gonna have to go look at that as well. So I am going to rename these Kubernetes contexts to not have the word kind in them because it saved me a lot of typing while I was doing this. Next up, one of the downsides of kind of pun not intended, is that it doesn't actually ship with a load balancer implementation internally. And this is a downside because if I'm working with multiple clusters and I'm trying to keep them all apart, I actually don't really like using port forwards because invariably I end up mistyping a context name and having bad things happen and getting very, very confused because I'm forwarding a port to the wrong machine. And it's just, this always ends up being a challenge for me to keep track of. So I'm actually going to go ahead and set up MetalLB on my clusters so that I can have them allocate real IP addresses and make it much more like what you would see if you were doing this in a cloud provider. This is the place where if you're using Docker Desktop on a Mac, this is probably not going to work very well, and I'm sorry about that. Use OrbStack instead. OrbStack is great. I'm going to go through this bit a little bit quickly because it is kind of departing from what we're really trying to demo very much. But you'll notice that if I look at my Docker network, I have two subnets. I have a v6 subnet and I have a v4 subnet. What I want to do is create three ranges in here, one with a 4 for the, actually, the one with a 4 will only be an IPv4. The one with a 6 in it will only be an IPv6. And the one with a 10, I need a 10 range in both of them. This turns out to be very challenging to do from the shell, so I'm doing it with a Python script where we just go ahead and read the ipam.config thing that we just looked at, split out the subnet, and then if the address ends in : it must be a v6 address, so we carve out a 6 and 10 96-bit range. If it ends in .0, it must be an IPv4 network, so we carve out two 228 bits. One of them ends in hex 40 and one of them ends in hex A0. A is 10, so these are where I get my 4 and 10. And then we have the Python script just go and hastily write out these MetalLB configurations. So if I run that, these are the ranges it ends up picking, and the MetalLB things look all the same, where the v4 one says, okay, this is the address range you get to assign load balancer services in. The v6 one is going to assign them in the v6 address that has a 6 in it. And in the dual cluster, we get two ranges that it can pick to choose for load balancers. So with that done, I'm just going to go ahead and quickly go through and install MetalLB in each of my clusters. And then wait for it to be ready. I swear every time I type rollout status in this demo, then it ends up taking just long enough that I get concerned about it.
Yep. That's what I call the driving down the road problem. When you think you already passed something, you have to be patient.
Yep. Totally real. All right. And then I'm going to go and apply those MetalLB configurations everywhere. So now my load balancer should be working. I'm going to go ahead and install the Faces demo. I'm going to tell the Faces demo that I want it to use a load balancer service for its GUI instead of a cluster IP, because this is taking long enough and I do not want to walk through configuring an Ingress controller separately. Pro tip, don't do this in practice in the real world. Letting you use a proper Ingress controller for this, right? But I'm also going to turn off errors because we're interested in poking at v6, not debugging Faces. And each of my clusters is going to be using a different color for the cells so that we can more easily tell them apart. My v4 only cluster will use red backgrounds. My v6 only cluster uses green backgrounds. Let me just get to the end of that. And my dual stack cluster uses the default blue backgrounds. The other thing I'm going to do here is I'm going to create a special service account for the Face workload in the dual stack cluster. And then I'm going to patch the deployment for the Face workload in the dual stack cluster to use that service account, because later I may use it for demonstrating authentication. And probably shortly after we're done with this demo, I'm going to hack up the Faces Helm chart so that I don't have to do that with a patch. So let's get face is running. Okay, and now what we're going to do is grab the external IP addresses of all of the services, one for each cluster, and look at them and then make sure that we can talk to them. So in my v4 world, the load balancer is at 192.168.237.64. That's an RFC 1918 address as well. My v6 only load balancer looks like that. I'm not going to read the whole thing, but I will note that it ends in a 6, which is how I set things up for my v6 only cluster. My dual stack seems to have picked an IPv6 address for its load balancer. You can see the 10 in there. And remember, in the dual stack world, unless you go to some trouble otherwise, you're going to prefer IPv6. So let me go ahead. Let's check those out in the browser. Here is my v4 only cluster. You can see if you look up here, that IP address, that's a v4 address. My v6 only cluster, which is green, we can see that there's a 6 in its address. And this is my dual stack cluster with the default blue that has a 10. So we can talk to all three of these. Everything is great. And it's kind of entertaining to note that in the process here, we have also demonstrated that my browser knows how to do IPv6, and my Macintosh knows how to do IPv6, and Docker knows how to do IPv6, and Kubernetes knows how to do IPv6. So, you know, turtles all the way down. Just being able to see this page in a web browser, there's a lot of things that have to work for that to happen. All right, next up, we're going to install Linkerd, and we're going to do it in a way that we can set up multi-cluster using multiple address families as well. So I'm going to go ahead and set up certificates to use. I'm not going to talk about these certificates because we talk about it in such great length in the multi-cluster SMAs. If you want more details about exactly what's going on here, I would point you to the multi-cluster SMA. But basically what we did was we created one trust anchor, and then we created an identity issuer cert for my v4 only cluster, and then one for my v6 only cluster, and then one for my dual stack cluster. Now when I install Linkerd, well, first we'll go ahead and make sure I've got the Linkerd CLI. I do, and I'm also using Edge 24.6.1, which is later than 24.5.5, so we're good to go. And when I install Linkerd into my v4 cluster, I will explicitly tell it to use the trust anchor I just created and to use the v4 issuer cert for its identity issuer. Yeah, the Edge Roundup from June talks about the differences in all these Edge releases. Okay, so we'll get that going. Normally, I would run Linkerd check at this point, but I am not going to do that now. I'm going to install Linkerd in the other clusters and then come back and run check on all three of them, so it's faster. The other thing worth noting is that in the IPv6 capable clusters, so the v6 only cluster and the dual stack cluster, I need to set this disable IPv6 to false when I install it, because otherwise Linkerd will not do IPv6, and that will not work all that well, especially in the v6 only cluster. So we'll get that going.
Is that for efficiency?
Is which for efficiency?
By skipping it by default, because most environments are IP4.
I think it's efficiency, but also because cloud providers that don't support v6, if we start trying to do v6 things, especially in the CNI,
yep,
they can get very unhappy with us.
Protective. Good.
So yeah. Okay, so once that's done, we will run Linkerd check in all three of these clusters. This is another point where, I don't know, if anything comes to mind, Tom, then now's a good time, because this takes longer than I want it to every single time.
Yeah, and I think, you know, having checks and balances, and again, we don't always want to necessarily enable everything, and this is a good point. Like, I was just thinking about it, that, you know, there's a reason we're doing that, and especially because some cloud providers don't have 6 support, and you don't want to be turning that on.
There's actually, I don't remember which release it is, but at least one of the Edge releases, we switched over to not recommended, because it makes GKE very, very unhappy if you're using the CNI, because it accidentally defaulted v6 to on in the CNI. Yeah. And I sit in on the same meetings, and I hear these things like every day, and I'm like,
I couldn't believe that such and such doesn't support IP6. I'm like, really?
So
What?
for Gateway API, I spend a fair amount of time talking with some of the folks over at Google and such. And
Yep.
It's really fascinating to kind of the perspective from inside the engineering world for one of the cloud providers is really different from the perspective from outside. It's kind of fascinating.
Yep.
All right. So now Linkerd is installed, and we're going to go ahead and mesh faces. This is exactly the normal way we always do this. We annotate the namespace with linkerd.io/inject equals enabled, and then we do a rollout restart. And we're going to do that. I just did that in the v4 cluster. Now I'm doing it in the v6 only cluster. And then I'm going to do it in the dual stack cluster. And then after that, I'll run rollout status in all three of them to make sure that they've restarted. And faces, thankfully, is fairly quick to restart. And it makes a liar out of me, but yeah, whatever. Okay. So we can see we've got 2 containers per pod in the v4 only cluster, and we've got 2 containers per pod in the v6 only cluster, and we've got 2 containers per pod in the dual stack cluster. And if we flip back over to the browser, then, absolutely nothing looks different because we've just meshed everything and it should still be working. So far, so good. All right, now it's time to start messing with things. If we look in our dual stack cluster, we will see that it has preferred IPv6 everywhere. So we will switch Smiley to use a v4 address, even though it's in the dual stack cluster, just to prove that this works. This turns out to be a little bit weird. You can't just use kubectl edit to do this because it's already attached the v6 addresses to it and the v6 address family to it. And it doesn't like to change that after creating it. So instead, we'll read it out with YAML, and then we'll edit the YAML. So we'll get rid of the creation timestamp and the resource version and the UID, but more importantly, we'll get rid of these cluster IPs, and then we'll mark the whole thing as IPv4 for the address family. You'll notice a single stack here. And we'll also go and get rid of need to. What's going on here since it's complaining about my connection being lost? Okay.
I thought it was my connection. I was worried there for a second.
Yeah. We don't know what it was. I just got a warning saying, oh, your connection was lost, but it looks like we're back. So good enough. All right. So now we have a smiley.yaml file with a v4 version of the Smiley service in it. So we will delete our original Smiley service and everything will break because there is no Smiley service for our Faces app to talk to.
Angry.
And now we will put back the Smiley service. And oh, look, it just works. Isn't that cool? If we read this back now, we can see that it's now using a cluster IP in the IPv4 family, not the IPv6 family. Oh, come on. Don't mess with me like that. So yeah, this is just basically demonstrating that our dual stack cluster is indeed a dual stack cluster. We can use both of these families and use it pretty seamlessly. This is also demonstrating, by the way, that the application, the Faces application is written in Go, and it's demonstrating that the Faces application is just doing the right thing by saying, hey, I want to talk to the service called Face and not particularly caring about the address family. This is why I say that the modern languages just do this pretty gracefully. Next up, we're going to do a minimal lockdown of the Faces namespace, by which I mean we are going to switch the whole namespace to having a default inbound policy of deny, which tells Linkerd that nothing gets to talk to it. If I do this, and then I restart all the pods in there, we will shortly see everything go to hell in a handbasket. There we go. So that's the face you get when the GUI actually can't even talk to the Face workload at this point. So nothing is going on. Nothing is working. And we will fix this by adding network authentication. So we're going to define a server that covers all of the workloads in the Faces namespace because they all happen to have that annotation, sorry, that label. We'll define a network authentication that says everything from our v6 range there, note the 10 is good. And then we'll do an authorization policy that says, okay, so if you're trying to talk to the faces server, which is to say any of the pods in that namespace, you need to be coming from a network authentication that matches this thing. And when I apply that, most things will start working again. But we still cannot talk to the smiley service. This is what I was talking about with being careful about ranges with network authentication and dual stack clusters. The smiley service is, again, in the v4 world. So we also need to add the v4 CIDR into our network authentication before this will work. And when I put that in, suddenly we can talk to everything again. So basically, this is kind of the only gotcha that I ran into, is that if you want to do network authentication in a dual stack cluster and you're actually using things in both IP families, then you need to make sure that you explicitly list both of those in network authentications. All right, that done. Let's see if we can do some multi-cluster stuff. I'm going to cheat slightly here. If you remember my multi-cluster thing where I was using K3D, K3D likes to set up a port forward on localhost for the API server, and so we have to do some special crap to make that work when we're doing multi-cluster. Kind, interestingly enough, does the same trick, but we really don't need to if we're using OrbStack, or if you're using a Linux box. We can just repoint the API server to the specific IP address and not go through that port forward. So that's what I'm doing here. Also notice that I have to use the name with kind in it here because I renamed the context, but I didn't rename the cluster. So once I do that, then it makes it easier to set up multi-cluster because I don't have to keep slapping around -- API server parameters on everything for multi-cluster. Also, we need to set up routing, and routing between these clusters is a little bit weird because from my v4 only cluster, I need to route to the dual stack v4 network. From my v6 only cluster, I need to route to the v6 network on the dual stack node. And then from the dual stack node, I need to route to both of those, but that's pretty easy. This is another thing where trying to grab all of this information with the shell is hard. So I'm not going to do it. Instead, I shall use another stupid Python script, which uses kubectl get node for the correct context and node name, spits it out as JSON, and then looks into, if I want it to give me a CIDR, it looks into spec.podciders. If I ask it for v4, it looks for the one that has a dot in it. If I ask it for v6, it looks for the one with a colon in it. Same thing, if I want node IP, it looks at status.addresses, finds the ones that are marked as internal IP, and then hauls out either the v4 version or the v6 version. The reason that this is hard to do in shell is that trying to get JQ to match everything up with those type equals internal IP things and also grab the one in the correct address family is a royal pain. So I shall run getinfo.py --CIDR --v4, and now I have the v4 CIDR for my v4 only cluster. I'll repeat that for the node IP. Then I'll do the same thing for my v6 pods, CIDR, and my v6 clusters node IP, and you'll notice that those are both v6 things. I have to do it twice for the dual pod, or sorry, I have to do it twice for my dual stack cluster to get the v4 pod CIDR and the v4 node IP, and the v6 CIDR, the v6 pod CIDR, and the v6 node IP. There's also a service CIDR, just to make all of this that much more complicated. And now, having done that, I can route from my v4 only, from the node in my v4 only cluster, back to the v4 address range in my dual stack cluster. I can repeat that for my v6 only cluster back to my dual stack cluster. And for my dual stack cluster to my v4 cluster, and my dual stack cluster to my v6 cluster. You'll note that I did not set up routing between the v4 only cluster and the v6 only cluster. A, I don't need it, but B, you can't do that. They don't speak a common address family. There is no way to route between them. That done, I can finally go set up multi-cluster. It's funny to go through all this because none of this is actually hard, but man, there are a lot of details, you know. So we'll do multi-cluster install in all three of the clusters. You'll also note that I'm doing this with -- gateway equals false. I'm going to do direct pod-to-pod multi-cluster for this. After I do that, I can run Linkerd multi-cluster check for each of them and see that it comes back and is happy. I love the fact that it comes back and is happy. Then I can do links. I'm going to link. What I'm doing here is I'm creating a link in the v4 only cluster and then applying that link in my dual stack cluster. So I'm linking from the dual stack cluster to the v4 cluster, from the dual stack cluster to the v6 cluster, because I'm going to mirror from the v4 and v6 back into dual stack, and that's it. And again, I have to do these link commands with -- gateway equals false. Once I do that, I can run multi-cluster check again in my dual stack cluster. And it works, which is really nice. Once the links are up, then I get to go and do mirroring. So I'm going to mirror the Smiley service from my v4 only cluster into my dual stack cluster. And I'm going to mirror the color service from my v6 only cluster into my dual stack cluster. And at this point, we should see all of those mirrored services magically appear. And in fact, I do. I see color SMA v6 and I see Smiley SMA v4. Interesting point. My mirrored Smiley SMA v4, you will note, has an IPv6 address, not an IPv4 address. But if I go and I explicitly ask Linkerd, hey, tell me what endpoints you know about for that mirrored service, it will come back and tell me, oh, look, I have a v4 endpoint. This is actually really fascinating because my application will end up trying to talk to Smiley SMA v4 using a v6 connection, which Linkerd will just turn into a v4 connection when it goes and talks to the other proxy. So there's some serious black magic happening under the hood here. But again, pretty much invisible in practice, which is amazing. All right, so time to break things again. Let's just delete the Smiley workload in our SMA dual, in the dual stack cluster, and watch everything break. Yeah. So we will use an HTTP route to take all the traffic that should be going to the Smiley service and route it over to Smiley SMA v4. And when we do that, then my demo breaks for no apparent reason.
Give it a second.
I just reloaded the browser window doing that. You know what? We're just going to talk for a minute and give it a second.
Yep. It's recycling everything.
I might also delete the route if it doesn't come back in a second or so and then reapply it. And I'm really loving things right now because I've done this in dry runs probably half a dozen times, 8 times, and it worked flawlessly every single time. But now it's just trying to mess with me.
Sometimes. Every once in a while. Okay. Let's see what you got.
Let's see what we do have, shall we? Is it there?
Faces. Namespace.
Thank you.
You're welcome.
Oh, hey, look, now it's working.
Just got to give it time.
So, like I said, it's working great, and I guess I'll be talking to engineering to try to figure out why exactly it should have taken much time there, because that's a little confusing. I'm not going to lie. But we now have things working, so that's good. Where were we in this demo? We just applied that, and let's try this again, but let's try a canary this time. And what we're going to do here is we will shift some traffic from, we're going to take some of the traffic going to the color service. We'll take 80% of it and shift it to the normal color service, and the other 20% we'll send over to the mirrored color SMA v6 in the v6 cluster. If you remember the v6 cluster, the color is green, not blue, so we'll be able to see some difference here too. And this one worked great just from the beginning. Okay, awesome. We can, of course, go through and edit this one. And, we'll do our usual bit where we switch to a 50-50 split, and then we can do a 20-80 split so it's mostly green. And then we can do a 0-100 split so that it's all green. And again, the kind of cool thing about this is that at this point, I've got the face workload running in my dual stack cluster, talking to the smiley workload in my v4 only cluster, and talking to the color workload in my v6 only cluster. And all of this just works. Continuing our trend of let's break some things, let's lock down the faces namespace in the v6 only cluster, which is the one where we're running the color workload, if you remember. So I'll do that in SMA v6. I'll then restart all the deployments in faces in v6. And as they finish, you're going to see, there we go. We can no longer talk to the color workload because I just switched it to deny everything. So I'm going to take advantage of that magic TLS, the special service account we created, right? So here, once again, same server definition where it's picking up all of the things that are in the faces namespace. I'm using a mesh TLS authentication for anything with the face SMA dual.faces.service account.identity.linkerd.cluster.local identity. And my authorization policy basically says, if you're trying to talk to the faces server, you have to use that TLS authentication that we just did. So when I apply this, and you'll note that I'm putting this in the SMA v6 cluster again. When I do this, it will magically start working again. So that's pretty much it. We've got Linkerd running in v4 only and v6 only and dual stack clusters. We've shown off some basic multi-cluster stuff, some authentication policy, some gateway API stuff. We've shown how to force a service to be v4 in a dual stack cluster. And we've also kind of shown that in general, this is pretty much invisible in operations. As always, you can reach me, Flynn at buoyant.io, or as Flynn on the Linkerd, really any of the Slacks associated with CNCF stuff. But that's it for the demo there. The Buoyant Linkerd forum, great place to post questions and get some answers. I don't know. I'm not seeing a bunch of questions right now. Anything come to mind, Tom, on your end?
No, it's a fantastic demo. I like how you dovetailed it into some other useful things as well. IPv6, again, it's that rolling freight train or the hurricane that we've seen heading to us for a long time. It's time to stop ignoring it, deal with it, right? I mean,
pretty much.
If you want to get rolled over, then that's fine if that's how you like things, right? But we've made it easy. We've taken a lot of the pain out of it, within your clusters. Again, check your provider, your underlying layers, and make sure that they support it and support it well. And, doesn't have to be scary.
It was really, really nice to do this one where, like I said, I first heard about V6 in the mid-90s, and I have played with it on and off for at least the last decade, probably longer. And one of the things that was really astonishing to come back to it this time around was like, oh, hey, like all the operating system stuff just supports it. And, there's just so much annoyances and pain from the last time I looked at it a few years back that's just gone now. And then seeing Linkerd do such a great job of making it pretty much invisible was really nice.
Yeah, I liked how, it does the translations and fixes things so that you don't have to worry
Yeah,
about, oh, now this isn't working. Why isn't it working? Right. It's little things that we can catch because we're
yeah,
controlling the traffic right there at the proxy. We can clean up and make decisions. So that's very
yeah.
nice.
I was kind of expecting that I was going to, I don't know, that I was going to see things where I had to think about what protocol family, what address family was in play, and it's just like, yeah, pretty much none of that. It's great.
Yep.
All right.
So next, we got something pretty exciting coming up. Multi-cluster, right? We're going to talk about some pretty big topics: disaster recovery, cloud migration, progressive delivery. This is all good stuff.
Yep. That's on July 18th. We're pretty much talking about really ways that you can use multi-cluster in practice other than, I mean, we show it off a lot doing silly things like, suppose we want to run this workload in a different cluster, which is not necessarily how you'd use it in practice. So we're going to talk about some things you can actually do with it in the real world.
Yeah.
Of these, cloud migration might be the one that I think might be the most fun personally, but whatever.
Well, multi-cloud too, right? And running
Yeah,
hybrid
yeah,
cloud situations where, you want to run some on-prem or you don't want to put certain things out there in the public cloud. This is I don't even want to call it a tool. It's, it's a part of Linkerd that breaks those boundaries and allows you to kind of embrace the best of the best. Or for folks who are thinking of FinOps or FinOps or however we want to say it, it's a big thing because you can start, the more we treat Kubernetes clusters as just another resource, you can start moving workloads around to fit, your cost models and to save money. And you combine that with things like Hazel and stuff, there's a chance to really cut a lot of cloud spend down, with these technologies.
And that one in July, we will be doing with Bell, and I expect we will have some pretty decent opportunities to show Hazel off too, which will be kind of fun.
Yeah. With flat network pod to pod, Hazel's fantastic thing. And again, you don't have to be running in cloud providers to get advantage out of keeping traffic in what you would call a zone. If you're completely bare metal, you can keep things in rack. If you have a top of rack switch for folks who are extremely latency aware, it's a great technology for that as well. It's not always about saving the dollars. It's about saving, milliseconds sometimes. So
yeah. There's a bunch of really cool stuff with that. If you have not yet tried out Bell Buoyant Enterprise for Linkerd, that's how, buoyant.io/enterprise-Linkerd. It's good stuff. I mean, I don't know what else we can say about that. Just,
yeah, you can go to enterprise.io and sign up and give it a try.
And start playing with it today. Yeah. Yep. And that is it. Unless folks have questions.
I am not seeing anything in the chat here.
That always makes me a little nervous, like
it works too well.
It's like, did I go too fast and lost everybody, or did I? All right. Well, I guess we'll hang on for another minute or so, just in case somebody's typing frantically. And other than that, if not, though, then we'll be back on July 18th to talk about multi-cluster stuff. The source code for this, as Tom has been showing a couple of times, is already up on GitHub. There we go, right there.
Yep, go dig through
Hopefully it'll work for other people. If you're on a Linux box, you should be good to go. If you're on a Mac, I strongly recommend checking out OrbStack for it.
Yep. Or get yourself a nice Linux box under your desk like I have. Yeah.
Well, you could do that.
It's helpful. Yeah. When you're beating on a problem and you're like, this is not working, that's what I do is I go down there. I'm like, all right, is it my Mac? Yeah. So I love my Mac, but
I can't just pick up my little rack of Raspberry Pis because it's plugged into an Ethernet cable, but that's, that's what I do.
Just mount them under your desk.
Honestly, what I want to do is design a proper PCB to hold them as a passive backplane.
Yep.
And the problem with that is that every time I start thinking about that, I start thinking I should just make it an active backplane with power management and stuff.
Well, and they keep upgrading them so fast that why would you want to build something that will be obsolete before?
I'm not interested in the compute module version of it. I'm
Yep.
thinking of the 40-pin GPIO header, which is much less likely to
No,
get vanish out from under me, right?
Yep.
Anyway, all right. I think we're good. Thanks much, Tom, and
Thank
we'll
you.
be back on July 18th.
See everybody then.